Okay, so we're going to compute the Fourier transform of a different function. So we computed the Fourier transform of the rectangle function. We're now going to compute the Fourier transform of this function. So we want to compute the Fourier transform. I'm going to write the function which we're computing the Fourier transform of. It's equal to e to the minus ax squared. If you're familiar with probability and stuff like that, this is, it's not quite a Gaussian because it needs to be normalized by something to make its integral equal to 0. But we will look through that we will look at that in just a minute here. Let me just write down this fact here. The integral of this function from minus infinity to positive infinity, e to the minus ax squared dx, this is equal to the square root of pi over a. Now why is that? Like, where does that come from? I'm not going to tell you where it comes from. I'm sorry, I'm not going to compute this integral for you, but I'll show you how you can compute it. If you haven't seen it before, I think it's a very nice exercise to do. We're actually going to compute the square of this integral, and I'm actually going to do something a little bit different. I'm just going to compute e to the minus x squared, and you can do u sub to figure out how to get it to this, or some other method to figure out how to get this fact here. So we're actually not going to compute e to the x, we're not going to compute this integral, we're going to compute this integral squared and then take the square root. So we're going to have something like this. But now I'm going to use a variable e to the minus y squared dy. Okay, this is just a number, this is just a number, this is the square of the thing that we care about. But now we can also think about this as an iterated integral in the xy plane. And this is the integral, let's say x going from minus infinity to positive infinity, x going minus infinity to positive infinity, e to the minus x squared plus y squared, dy dx. Now, the difficulty with this integral is that there is not an antiderivative of e to the minus x squared. The difficulty with this integral is that there's not an antiderivative of e to the minus x squared. Notice if we change this to polar coordinates, what's going to happen, we're going to get e to the minus r squared there, but the differential becomes r d theta. So we have e to the minus r squared times r d theta, and now we can use u sub because we have e to the minus r squared times r. Okay, so that's a little trick. If you haven't seen that before, if you haven't done that computation before, it's a very nice computation. It seems like we're sort of doing, it seems like a trick here, right? But think through that if you haven't seen it before. Talk about it in the discussions as well. Okay, so without further ado, we're going to compute the Fourier transform. I hope it's clear that this function is absolutely integrable because it's a Gaussian, it's a negative exponential, it decays very quickly. So the formula then for the Fourier transform is f hat of omega is equal to 1 over the square root of 2 pi. I get this 1 over the square root of 2 pi. I like that I have that in the definition. I mean, I think it belongs, and we'll see why when we look at, we'll see why I'm saying that when we look at the inverse Fourier transform. But I sometimes forget to write it in the notes. I try not to do that, but I sometimes forget to write it in the notes. Okay, so this is e to the minus ax squared times e to the minus I omega x dx. Okay, this is probably going to be a long video, a somewhat long computation. It's mostly straightforward. There's just some little things you got to do here. Okay, now, since this is an exponential, this is 1 over the square root of 2 pi. There's the integral from minus infinity to positive infinity. Combine this now into one exponent, and it's going to be minus ax squared plus I omega x dx. Okay, so what I just wrote, you've got 1 over the square root of 2 pi. And then we have the integral. The integral goes from minus infinity to positive infinity, and we're integrating an exponential function. And the thing in the exponent is minus, and then parentheses here, ax squared plus I omega x. Okay, so now what I'm going to do, I'm going to do a little scratch work down here. Well, let me actually, well, let me take one more step. So this is 1 over the square root of 2 pi. Everything is how I had it before. I'm just going to develop this exponential. So I'm going to factor out an a here. So now everything is the same, but I'm just writing it a little bit differently. In the exponential now, it's minus a times x squared, and I have to divide this second term, so it's going to be plus I omega over a times x dx. Okay, so now what I'm going to do is I'm going to complete the square here. I'm going to complete the square in the exponent here. And so what this is going to become, I have x squared plus I omega over a. I'm just going to write down what this is equal to by completing the square. It's going to be x plus I omega over 2a squared. Then it's going to be minus I omega over 2a squared. So that's going to be minus I squared, but I squared is 1, so it's going to be plus omega squared over 4a squared. Okay, so now what I have, the exponent is minus a, then it's going to be minus a times what I'm about to say. X plus I omega over 2a, that whole quantity squared, plus omega squared over 4a squared. And so this is equal to 1 over the square root of 2 pi, and then we're going to have the integral. I know I'm probably in the way, but I'll step out in just a minute. X going from minus infinity to positive infinity of e to the minus a. Okay, it's going to be e to the minus a times x, x plus I omega over 2a squared. Okay, then it's going to be a times omega squared over 4a squared. And what that's going to end up being is just minus omega squared over 4a dx. So let me just read what I have here. The Fourier transform of the function in question is 1 over the square root of 2 pi times the integral going from minus infinity to positive infinity. And the function we're integrating is an exponential function. And in the exponent, we have minus a times this quantity here. It's x plus I omega over 2a, that whole thing squared, and then minus omega squared over 4a. Okay, so I'm going to erase these two lines here, okay? And then I'm just going to copy that up there. So I'm going to erase these two lines. So pause the video if you haven't written this down, and maybe you should now. Okay, so I'm just going to copy that up here. I wish I had like a smart board or something where I could just like copy and paste this up there, but I don't. In fact, the board I have now is not, I wanted a chalkboard. I wanted a chalkboard for a number of reasons, but I think the glare with this board is not so good, or it's bad, I guess. Okay, so notice I have e to the minus omega squared over 4a. That doesn't have anything to do with x, so I'm actually going to pull that out. So this is, on the outside of the integral, we're going to have an e to the minus omega squared over 4a. Then we're going to have an integral x equals minus infinity to positive infinity e to the minus a x, I keep writing it t for some reason, x plus I omega over 2a squared dx. So let me just read what I have here. Well, let me erase this part first. So I've got 1 over the square root of 2 pi times e to the power of minus omega squared over 4a. And then the integral going from minus infinity to positive infinity. Sorry, I need to shake my mouse. The integral going from minus infinity to positive infinity. We're integrating an exponential function, and in the exponent it's minus a, open parentheses, x plus I omega over 2a, close parentheses, squared. Okay, well this is good, because what we're going to do, we're going to do a u sub here. We're going to say that u is equal to x plus I omega over 2a. Now this, what we're doing is we're just shifting this in the complex plane, and a similar computation to what we did over here will show that if our limits, will show that it's equal to this. Hold on. This is equal to 1 over the square root of 2 pi times e to the minus omega squared over 4a. This is still going to be, the limits are going to be the same, sorry, but they're u now. U going from minus infinity to positive infinity, e to the minus a times u du. Sorry, okay. Really, so when we're integrating this, these two, everything I wrote here is correct, but I just want to point out, really what we're doing is we're integrating from like, we're integrating in the complex plane horizontally at the height, or at the imaginary level, omega over 2a. Sorry, there's a squared here. Apply this same computation, you'll get this. Another way to think about this is when we're integrating e to the minus ax squared over the complex plane, this is like the integral centered at 0. This is just the integral but centered at a different point. So instead of being centered at 0, it's centered at the up on the imaginary axis at I omega over 2a. And so it's going to, since you're still integrating over this whole complex plane, it's still going to be equal to each other. We're just like, this is a Gaussian, okay, and then we're just shifting it so that it's, okay, maybe that's too much explanation there. In this context over here, okay. Like in this context here, what we're integrating, well, sorry, I think I've said too much. All right, at any rate, this is equal to 1 over the square root of 2 pi times e to the minus omega squared over 4a, and this right here is equal to the square root of pi over a. Okay, and so now what we're going to get is, so notice what's going to happen. I've got a square root of pi over square root of pi, and so what we're going to end up with is going to be equal to 1 over the square root of 2a times e to the minus omega squared over 4a. Okay, just want to make sure, yes. Okay, so the Fourier transform of e to the minus ax squared is equal to 1 over the square root of 2a times e to the minus x squared over 4a. Okay. Let's try to do something similar here. So I'm going to erase this here. Typically, you might remember, like from differential equations, the thing that we often care about is not necessarily going from a function to its Laplace transform, but from the Laplace transform back to the function. In other words, doing the inverse Laplace transform. Now, we're actually kind of unlike with Laplace transforms. Fourier transforms have an integral formula that's very similar for the inverse Fourier transform, but we don't always have to use that. So let's say we have a function and we know its Fourier transform. We know that the Fourier transform of the function is equal to e to the minus t omega squared. This will come up a lot. Things like this will come up a lot. Let's say we have a Fourier transform and we know its Fourier transform is e to the minus t omega squared. So e to the minus t omega squared. What we want to do, so let me actually, hold on a second. Let me denote this a little bit better. F of x is equal to that. F hat of omega is equal to 1 over the square root of 2a times e to the minus omega squared over 4a. So let's keep that here, and let me do the other example on this side. I was using f. I was overloading f, I guess. All right. So now what we want to do is we want to find the inverse Fourier transform of e to the minus t omega squared. Okay, now what I'm going to do is I'm going to look over here. Okay, the inverse Fourier transform of this function is equal to e to the minus ax squared. So these are similar. So notice it's similar in the sense that we have a negative exponent, an exponential with a negative exponent. So if I look over here, I could say the inverse Fourier transform of e to the minus omega squared over 4a is equal to the square root of 2a times e to the minus ax squared. So the inverse Fourier transform of 1 over the square root of 2a times e to the minus omega squared over 4a is equal to e to the minus ax squared. But if I just multiply both sides by the square root of 2a, it says the inverse Fourier transform of e to the minus omega squared over 4a is equal to the square root of 2a times e to the minus ax squared. And I want to use this fact over there. So I'm starting with this, and if I kind of compare these two things, it looks like I need to have t is equal to 1 over 4a, or this is equivalent to saying a is equal to 1 over 4t. So the inverse Fourier transform, which I'm just going to call IFT for now, inverse Fourier transform of e to the minus t omega squared is, well, it's going to be this formula here, but wherever I see an a, I'm going to put 1 over 4t. So the square root of 2a, that's going to be the square root of 2 times 1 over 4t. And then e to the minus ax squared, if a is 1 over 4t, this is going to be e to the minus x squared over 4t. And I can simplify this a little bit. 2 over 4, that's 1/2. So this is 1 over the square root of 2t times e to the minus x squared over 4t. Okay, so that's what we have. The inverse Fourier transform of e to the minus t omega squared is equal to 1 over the square root of 2t times e to the minus x squared 4t. And now I'm going to give one more way to show this Fourier transform. So this is showing the Fourier transform of this function in two different ways. Okay, and the reason I like the way that I'm about to show it is because it's going to sort of, well, we're going to solve an ordinary differential. We're going to solve an ordinary differential equation to find the Fourier transform of this. Okay, I hope you will like this. Okay, so first I want to observe that this is my f of x, e to the minus ax squared. Notice that f prime plus, let me write the argument, f prime of x plus 2ax, f of x is equal to 0. F prime of x plus 2ax, f of x is equal to 0. Okay, and so now what we want to do, sorry, I keep having to come over here. Okay, we're going to take the Fourier transforms of both sides of this equation. So it's very similar. Notice it's a differential equation in the x variable. We're going to take the Fourier transform. Okay, now when we take the Fourier transform, what we're going to end up with is the following. F prime of x, okay, when I take the Fourier transform of f prime of x, I'm going to end up with I omega f hat of omega. Okay, and over here, the Fourier transform of x, f of x, is I times the derivative of the Fourier transform. So this is going to be plus 2a I times the derivative of the Fourier transform, and that's equal to 0. Okay, so now I want to think about solving this differential equation. Well, notice I've got an I on both terms, so I can get rid of that. So this is going to tell me f hat of omega is equal, not equal, plus 2a, sorry, there's an omega here, omega f hat of omega plus 2a f hat prime of omega is equal to 0. Okay, so let's see what I can do here. Well, notice this tells me that f hat prime of omega over f hat of omega. Okay, so what's that going to be equal to? So if I divide by f hat of omega, I'm going to have that. Then I'm just going to be equal to minus omega over 2a. If I divide both sides by f hat of omega, it's just 0 over there. I've got f hat prime over f hat. I subtract the omega, then divide by 2. Okay, well this is good because this is the derivative with respect to omega of the log. Here log means natural log of f hat of omega, and over here this is equal to minus omega over 2a. Okay, so now again, this is just a differential equation. When I get into this point here, this is just a first order linear differential equation. You can solve it a number of ways. I'm going to solve it this way here. Okay, so now I'm going to take the antiderivative of both sides, and on the left hand side we're going to get log f hat of omega. Okay, what do we get on the right hand side? Well, I'm doing the antiderivative with respect to omega. So it's going to be equal to minus omega squared over 2a plus c. Okay, so I'm going to erase these lines here and just write my expression for log up here, or for log of f hat of omega up here. So what this tells me then is log, again this is natural log of f hat of omega is equal to minus omega squared over 2a plus c. Okay, now I'm going to raise both sides to the power of e, or sorry, raise e to the power of both sides. And on the left hand side, we're going to have f hat of omega. And on the right hand side, well, we're going to have e to the power of c. That's just another constant. I'm going to call it capital A. And then over here, we're going to get e to the minus omega squared over 2a. Sorry, some of you are probably screaming at me now. Sorry, I'm only recognizing it now, but I'm not making the whole video. When I did the antiderivative here, I need to divide by 2. And so that's going to be a 4 here, and we're going to have a 4 here. I hope I remember to put in the notes. I make a mistake when I do the antiderivative. Don't, because I know it can be frustrating. I know it can be frustrating when a mistake is made and you're not sure, is it the professor or did I just miss something? But in this case, it was the professor. Okay. So now what is this a equal to? I need to figure out what this a is equal to. Well, that's going to be f hat of omega, or sorry, f hat of 0. So f hat of 0, this is the Fourier transform of my function, but when omega is equal to 0. That's equal to a. That's just because if I put omega 0 there, this is 1, and so f hat of 0, so a is equal to f hat of 0. Well, what is f hat of 0 equal to? Well, just by the formula, this is going to be 1 over the square root of 2 pi times the integral going from x equals minus infinity to positive infinity, e to the minus ax squared. Okay, this is going to be e to the minus I omega x dx, but omega is equal to 0. So that's just a 0. So what I have, so f hat of 0 is equal to the integral, 1 over the square root of 2 pi times the integral going from x goes from minus infinity to positive infinity, just of e to the minus ax squared. Because when omega is equal to 0, this part's equal to 1. And so this is dx. Okay, now we can use the fact, I erased the integral, but we can use the fact that the integral of this function right here is equal to the square root of pi over a. So this is equal to 1 over the square root of 2 pi times the square root of pi over the square root of a. And that just becomes this, the pi's cancel again, and we have 1 over the square root of 2a. And so this is equal to 1 over the square root of 2a e to the minus omega squared over 4a. And so that is exactly what we got over here. This way is kind of, it's less straightforward. We're not computing the Fourier transform directly. We're kind of using this fact here. I got this from a book. This was not my idea to do it this way. I got this from a book by Rustam Choksi. It was a book that I've used before for this class. So this was not my idea to do it this way. But the one thing that I do like about it, I mean, the thing that I don't like about it is because it kind of, you have to kind of understand this. There's nothing wrong with that, but it's not straightforward, right? It's not just a straightforward computation of the Fourier transform. The part I like about it is I kind of just wave my hand over this complex contour integration in the plane, and I don't typically like to do that. But anyways, okay, either way, this is the Fourier transform. Two different ways of computing it, but this is the Fourier transform of this function. The other thing to point out is that the Fourier transform of a Gaussian, that is a negative exponential with an x squared here, is another Gaussian. So this is a very important property in this class and in terms of probability, and it starts to actually show some connections between certain PDEs and probability. Okay, I told you this was going to be a long video. It's almost 30 minutes long. That's it for this video.